So in this question, we have two metal cubes of different mass, initially at rest, on a surface with friction. They're also electrically neutral to start. So we're given the two masses, which are different. One has 2 gram, the other has 4 gram mass, and they're 6 centimeters apart. They're being then charged, so electrically charged at a rate of 7 nanocoulomb per second. So that means they're going to have the same charge, which means there'll be an increasing electrical force trying to push them apart. Because they'll have the same charge, it'll be repulsive. So the question is, how long after this charging begins does one cube begin to slide away? And it says which cube moves first. And that's really what we should use as our starting point. Just imagining what's going to happen, why, and look at our path to answering that initial question, which is our delta t. Okay, so which cube moves first? Well, we imagine that they're getting charged, They will immediately feel an electric force, but they'll be held in their current place by the force of friction. And we have a mu value, our coefficient of static friction here. Okay, so eventually, though, that force from the charge will overwhelm that force due to static friction, and one of them will move. But will it be the smaller one or the bigger one? They'll both experience the same electric force, so it'll be the smaller of the two. So M1 will move first because it has a smaller mass, so it'll have a smaller friction force here. Okay, so how long is that going to take? Well, our information here is that we've been given the charging rate, which I've written out as dq dt, so 7 nanocoulomb per second. That's a rate, so we should be able to get the time. If we knew the charge at which you would overwhelm the force of friction, we'd know when to look for. So let's take a look at what I mean by that. Okay. So what are we going to do? Well, we can also imagine, this dq dt, like, okay, so if we knew at what q we were going to have motion, and we know the rate at which, we're adding q, then we could solve for t. Because our dq dt, we can kind of think about it as a change in q divided by a change in t. And we've been given that, right? We've been given that 7 nanocoulomb per second. And so we want to find this delta t. So to get there, we're going to need this q. We're starting at 0, so let's find, to start, we'll find this q, at which point we are causing the M1 to move. Okay. So we know that the lighter cube moves first. So lighter cube will move first. And that's M1. And M1 will move. So M1 will move when the electric force is larger than the force of friction that's holding it in place. So when F electric is larger than the force of friction holding it in place. So what we're going to find first is we're going to find Q, kind of the threshold. We're going to find the Q threshold at which the F electric is kind of greater than or equal to, because equal to would be the threshold. you add one more bit of charge and it will be larger. So we're going to find the equal to, and then we'll find how long it takes to get there. And we'll find delta t. So this will be, we'll do this first, we'll do that second, find delta t to get to q given that rate of change, given our dq dt. All right, so let's do that. So step number one, we're going to look at electric force equal to force of friction static. And our force of friction static, if we remember, is our mu normal force. And the normal force here, if we're thinking about our blocks and all the different forces on them, normal force will just be equal to mg for each of those blocks. Okay, so I'm just going to go down here. This will be mu mg. And on the electric side, we'll use Coulomb's constant for simplicity. It'll be K Q1 Q2 divided by that distance between the blocks squared. Now we know that it's M1, so I'll just make that clarification. It's M1G. And then on the other side, we also know that it's Q1 is equal to Q2. So it's just Q squared divided by d squared. All right, so now what we need to do is isolate Q, which is what we're trying to find. And so I'm just going to write Q is equal to, well, we start with mu m1 g, and we're going to bring d squared up, so d squared, and then divided by, we've got k. Now to get rid of the square on Q, we're just going to have the square root of both sides, so square root here on these terms. All right, now all of these variables we have values for, so let's just give ourselves some extra room. So Q is equal to mu, that was 0.65, M1 was 2 grams, so that's 0.002 kilograms. G is 9.8 meters per second squared. And the distance apart was 6 centimeters. So 0.06 meters. That's squared. And then we have Coulomb's constant. I mean, that's formally, I guess that's 8.99 times 10 to the 9. It's fine. We're going to say for easier use, 9 times 10 to the 9. That's a lot easier to remember. Newtons meters squared per Coulomb squared. All right, and then that whole thing is under the square root, or to the 1/2. Okay, so if you go to your calculator and you plug those numbers in, you should get 7.14 times 10 to the negative 8, and that is in coulombs. Now, it's more natural to the scale of the question to move this answer to nanocoulombs. So nanocoulombs, nano is 10 to the negative 9. So that's our scale. And we're pretty close to that. We're at negative 8. So that means that our Q value, our charge, and I'll just write 71 because we're keeping two significant digits. So this would be like, so 71, and there's no times 10 factor. This is just 71 nanocoulomb is our answer. Okay, so we know our threshold charge. If you get to, you charge it up. Once we get to this amount of charge, then M1 is going to move. Okay, so now, but really what we wanted to know was how long until we get there. So let's do that now. We've got a dq dt, and so we said, well, our dq by dt is, that's basically our change in q over our change in time. And so we could rearrange that for delta t and say, well, delta t is equal to our change in our charge divided by this dq dt. And the change in the charge is what we just found here, 71 nanocoulombs. So we go from 0 to 71 nanocoulombs, and then our change was 7.0 nanocoulombs per second. All right, well, that is effectively 10 seconds. 10 seconds. Or if we wanted to be unambiguous about our significant figures, there's 2 in this question, so we would say 1.0 times 10 to the 1. That's unambiguous. 10 would be ambiguous. We wouldn't be sure if it was 1 or 2. So there's our answer. So it takes 10 seconds to reach this charge, and when we get to this charge, 71 nanocoulombs, M1 will move because the electric force will be larger than that force of friction. That's it.